So far we looked at a little bit of the dynamics, the kinematics and dynamics of a system of particles, of individual particles in an external force, and a few aspects of what happens when particles are in interaction with each other and what the dynamical equations or equations of motion look like. We also went on and looked at a case where you had a continuous medium such as a string under tension, and we saw what its equation of motion would look like, and in general it was the wave equation that we obtained for the displacement transverse vibrations of a string. We also saw very briefly what happens when you have a 3-dimensional medium such as air and you set up pressure waves in it which manifest themselves as sound, and we saw a few aspects of what happens there and wrote down the corresponding wave equation. In the same logical progression, we would now like to go on and study the dynamics of a continuous medium such as a fluid when it is in motion. So, for the next few modules we will look at fluid dynamics, namely the most elementary aspects of a fluid in motion as a continuous medium. Now, because it is a continuous medium, we have certain very special features which arise in the motion of this system, of such a system, which I will try to emphasize here. I must say right away that we are not going to look at fluid dynamics at the atomic or molecular level, because we know ultimately the fluid is composed of individual molecules which move around in close interaction with each other. We are not going to get to that level of description. We are going to look at it at a more coarse grained or rougher level, where we will talk about infinitesimal fluid elements as if they were all part of a continuous medium. So, we will not go to the atomic level, but we will look at it effectively at a much more coarse level, which is good enough for understanding fluid dynamics as it manifests itself in normal life. Now, there are several aspects to this, and there is something that I want to say right in the beginning, which is that fluid dynamics offers a very natural and physically intuitive way of understanding many concepts of vector calculus. And in fact, vector calculus to some extent was derived or invented, if you like, with the specific purpose of applying it to fluid dynamics. So, this gives us an opportunity to understand certain concepts in vector calculus such as the gradient and the divergence and the curl and so on, which really are part of a formal mathematical structure called vector calculus, but the physical interpretations of these objects, of these various quantities, is so simple and so straightforward that it is actually worth understanding it in the context of fluid dynamics, which is what we are going to do. As always, this is going to be pitched at a slightly higher level than is generally the case at the high school level or even the beginning undergraduate level, but I hope that we will make things very clear, physically intuitive, in a physically intuitive way, so that there should be no difficulty in understanding it as long as one understands the elementary operations of the calculus. Okay. So, let us start by asking how one would describe a continuous medium such as a fluid. So, you have a fluid in some container perhaps, and I would like to understand what happens to this fluid, or maybe it is in motion in a pipe of some kind, and we would like to understand what the flow is like, what the equations of motion are like, etc. Now, there are two ways in which you can approach a fluid dynamical problem. One of them is the Lagrangian method, where imagine that you have a medium. So, there is fluid everywhere and you focus on a particular fluid element at some instant of time, and then follow the path of this fluid element as a function of time. And you really have to do this for all the fluid elements in the fluid, allowing for various constraints such as the fact that two fluid elements can't sit on top of each other, etc. And this approach is called the Lagrangian approach. Where you focus on any given individual fluid element and watch its motion as a function of time through the fluid. On the other hand, there is another approach to it, which is the following: we focus on a particular location. So, I focus on a location whose coordinate is r and look at what sort of flow you have at that point at any instant of time. So, it is possible that at some instant of time this the element, the velocity vector at this point points like this, and of course it should be part of some continuous curve, and at a later instant of time it is possible that the flow changes in such a way that this velocity vector points like this and so on. So the idea is to focus on a location rather than an individual fluid element, and the two approaches are related to each other. This second approach is called the Eulerian approach. And that is the one in which it is easiest to write things down specifically, especially at an elementary level, and therefore we will look at the Eulerian approach. Okay. Then what are the variables that would describe an element of fluid at this location at any instant of time? Well, in the case of particles you talk about the position of the particle in all three Cartesian coordinates, for instance, plus the momentum of the particle or the velocity of the particle at any given instant of time, and you do this for each particle in the system. Here what we do is to associate with any point in the fluid a density rho, which could be a function of time because the fluid could be compressible and the fluid could be inhomogeneous. In other words, there could be different densities at different points in general. So the density, the pressure of the fluid at that point, P of r and t, and the velocity at that point, and I will use the symbol v as a function of r and t. I emphasize once again that by this v I do not mean the velocity of any individual fluid element in particular. I mean the velocity of the fluid, the velocity field of the fluid at the point r at a given time t. So at different times different parcels or different elements of fluid would occupy the location r, and I am talking about the velocity of anything that occupies the location r at time t. So these are the dynamical variables in the system to describe a fluid, and what we need to know is to determine, what we need to find is to find all these quantities given certain inputs, which would be like conservation of matter, conservation of momentum, the equation of motion of a fluid element, and so on. So we will do that systematically, but these are the unknowns. In fact, in general one is told what the pressure gradient is or what the pressure is. If you are given this field, then the task is to determine this and that. So that is the general problem of fluid dynamics in the Euler approach, namely given the external forces on the fluid, the pressure of the fluid, the pressure heads and so on, determine the local density and the local velocity. You need a sufficient number of equations to do this. Now this is a scalar quantity, that is important to remember, and that is a vector quantity of course. So the fluid's state is determined by a space and time dependent scalar field rho and a space and time dependent vector field, the velocity, as a function of space and time coordinates. So that is the general problem that we are going to tackle, or at least formulate in trying to understand fluid dynamics. But let us first look at a much simpler case, namely that of equilibrium, hydrostatic equilibrium. So I have in mind a fluid in some container which is completely at rest, nothing is moving, every element is at rest, and I would like to know what is the condition for this hydrostatic equilibrium. You know that the condition for equilibrium in mechanics for a single particle would be to say, or a body, given body would be to say, the net force on this body must be 0, and if it is initially at rest, then by the first law it continues to be at rest. A similar constraint, a similar condition of hydrostatic equilibrium is what we seek, and for this purpose let us set up a coordinate system somewhere, completely arbitrary where you choose it, right? And let us look at some given fluid element at the position vector r, and let us take this element to be at this position r, which is at the point which has got Cartesian coordinates x, y and z, and ask, in this case, what is the condition for this element to be at rest? Well, there is a pressure acting on this fluid. So, there is a pressure acting in this direction like this, from all directions there is a pressure acting on it. So, from the front and from the rear, this fashion. And let us look at the y component of this pressure. The pressure at the point R is P of R, and that stands for x, y and z. But if this line element is dy, this is dx and that is dz, infinitesimal volume element of volume dV. So, let us write dV equal to dx dy dz. Then from the left you have a force pushing in the plus Ey direction. So, this is equal to Ey, sorry, from the left you have Ey times P of R minus, because this face is dy over 2 to the left of the point x, y, z. So, this is equal to dy over 2 multiplied by the derivative of this pressure with respect to y. So, I do a Taylor expansion of the pressure at this on this face about the pressure in the middle of the volume element, and the first term is the pressure at that reference point minus the correction which is proportional to the increment, length increment, which is dy over 2 because it is halfway down, and then multiplied by the derivative with respect to y of the pressure itself. And this must be multiplied by dx, sorry, by dx dz, because that is the area of this element here. The vertical is dz and the horizontal going into the board is dx. And the pressure, of course, is the force per unit area. You can see that this multiplied by that is a force, has physical dimensions of force. That is the force appearing from the left, but that is compensated partly by the force from the right here, and that force is minus Ey, again P of R, but this time with a plus dy over 2, because this front face is dy over 2 removed in the y direction, positive y direction from the center of the cube, times again the derivative dx dz, and when you add these two, the net force in the y direction of this element is equal to minus Ey delta p over delta y times dx dy dz, which is equal to minus Ey delta p over delta y times dV. So, that is the y component of this force, and exactly the same sort of argument will tell you that the z and x components are respectively given by the same things with Ez delta p over delta z and Ex delta p over delta x. Therefore, the net force, the force I should say, the force on the volume element dV is given by a sum of all these three quantities minus Ex delta p over delta x plus Ey delta p over delta y plus Ez delta p over delta z times dV. Physical dimensions are okay because this is force per unit volume, and this here is a gradient force per unit area, and this gives you 1 over length once again multiplied by a volume element gives you a force, physical dimensions of force. So, this quantity is the force on the volume element dV. Now, this looks very much like you take the quantity p, which is a scalar function. So, remember that p is a scalar. It is a scalar function, the pressure is a scalar, but you take its derivative with respect to each of the coordinates on which it depends, and you multiply by the corresponding unit vector in this direction. Now this quantity has a physical significance which we will see in a second, and it has got a name. This thing is called the gradient of the pressure P. It is a vector, and the idea of a gradient, this is a natural place to introduce it, so let us do that. If you give me a scalar function phi of x, y and z, any scalar function of the 3 coordinates, then I can construct, just as I define the position vector to be Ex times x plus Ey times y plus Ez times z, what I can do with this quantity is to construct partial derivatives So I can find the rate of change of this function here at any point with respect to each of the 3 independent coordinates x, y and z, keeping the other 2 constant. So I move in the x direction by dx and find out how much it changes and so on, and I get this times dx, this times dy, that times dz, and I can construct a vector from this quantity which is defined in this fashion. And this is by definition, this is the definition of the so called gradient, which is denoted by this symbol here, the Greek symbol lambda of phi, which of course is a function of r. This is called the gradient of phi. So the gradient produces a vector function from a scalar function. A vector function of the coordinates is produced from a scalar function of the coordinates by this operation here of differentiating with respect to each of the independent coordinates, multiplying by the corresponding unit vector, and it is some kind of vector. Now the question is, what is the meaning of this vector? What does this gradient actually tell us? Well, it is not hard to see that it tells us what the rate of change of this function is in any direction whatsoever. So if I start with some point r in space and there is a neighboring point r plus dr in this fashion, then I could ask, if you have a phi which is a function of r and it has some value here and this phi has some other value at this point, how much does this phi change by? So if this is phi and this is phi plus d phi, I could ask, what is d phi equal to? Clearly d phi is going to depend on in which direction you move away from r. So even for a given distance from r, if you move in any direction in space, you may have a different d phi at each of these points. But you see, if you give me a dr, then I can always write it in the form dr is Ex times dx plus Ey times dy plus Ez times dz, and then it is immediately clear that if I define the gradient in this fashion, grad phi dotted with dr well, one should strictly speaking put a vector symbol on this triangle here on this delta, but I will not do so because it is understood that this is a vector quantity. So I do not need to put this delta each time. Since I cannot write in boldface, I am just going to leave it without an arrow. This quantity here, if I use the rule for cross products, the x of this with the x of that, the y of this with the y of that and so on, this as you can see is immediately equal to delta phi over delta x dx plus delta phi over delta y dy plus delta phi over delta z dz. But this is the total change in phi. By definition, if phi is a function of x, y, z, then the change in phi d phi along any direction is resolved into components. This is the change if you move only in the x direction, only in the y, only in the z direction, but to go to this point you have to do a little x excursion, little z excursion, little y excursion to go there, and this is the net change here. So by definition this is equal to d phi. In other words, the gradient of a scalar function dotted with the infinitesimal displacement dr gives you the change in the function when you move from r to r plus dr. So it actually gives you the change of the function in any direction in space, which is why the gradient is called the directional derivative or directional if you need to find out what is the rate of change of this phi along any direction, then what you have to do is to dot this gradient of phi with the unit vector in that direction and you have the rate of change. Okay. In other words, if you have a phi and it changes along some direction specified by the unit vector n, then this is equal to grad phi dot n. Yeah. So that is the meaning of the gradient of any scalar function. Now one could ask for a geometrical meaning. In addition to this, one could ask, is there a physical meaning of some kind, and the answer is yes, and it is very simply understood if you look at not a function of 3 variables for which it is hard for me to draw pictures, but let us look at a function of 2 variables. Let us suppose that you have a hilly terrain on the surface of this earth, which I will assume to be plane for the moment, and I have a hilly terrain at which for each x and y horizontal coordinates I have a certain given height. So it is like a mountain range. It is like some kind of complicated mountain range of this kind, and on this mountain range you would have seen there are contour maps which tell you all points of the same height. So all points of the same height, same given height, form a contour map, and if you look at it from above, the contour map is going to look like this. So that is the peak, and then you have points of equal height in the xy plane which look like this, etc., and that is the peak looking at it from above. So we are now in the xy plane and z, the height is coming out, and this is an equal contour map which says the height at a point x comma y along this curve is some constant equal to h1, some height h1. On this contour the height as a function of x comma y is h2, some other height, and so on till you hit the peak here at this point. Then you can ask, what does the gradient of this h look like? So it is clear that gradient of h of x comma y in this case is just ex delta h over delta x plus ey delta h over delta y at any point. So the question is, what is the direction of this gradient? The magnitude is trivial, it is square root of this squared plus that squared, but what is the direction of it? Well, it is clear that if you move along this curve, the height does not change at all. So it is not contributing to the gradient at all. On the other hand, if you move normal to it, that is what is going to contribute the maximum to the gradient, because if you move in any other direction like this, you can resolve it into motion along the contour and perpendicular to the contour, and along the contour there is no change at all. So it is only the perpendicular component that contributes to the gradient. Therefore, the gradient of a scalar function is in the direction in which the function increases in magnitude, increases the most steeply. In other words, this is the steepest way to climb the mountain. Normally you take a winding path to climb up, but if you did this, you go straight up the gradient, the maximum possible steepness here. So the physical, the geometrical idea of the gradient of a scalar function delta phi in 3 dimensions, for example, is directed along the direction in which phi increases most rapidly as a function of space coordinates for a given time, if it is a function of time as well. So that is the geometrical meaning of a gradient, that the level surfaces of a function in 3 dimensions, for instance, it would be some plane which would say phi of x, y, z, phi of r equal to constant, then along this surface phi does not change at all and the gradient points normal to the surface. This is the direction of grad phi. Just as if you had a function of two variables, the level curves of this function are h of x y equal to constant and the gradient points normal to that level curve, those level curves at any point. Similarly, the direction of gradient phi in 3 dimensions is normal to the level surfaces phi of x y z equal to constant at any point. And what we have just discovered is that the pressure, the force on this liquid we have just discovered on a volume element P. So force on a volume element P delta V dV is minus the gradient of the pressure at that point, or could be a function of T, but for the moment let us just look at it like this, it is a static case, times EV. Now if there is an external pressure on the external force on this, which is the general case, for instance you put a fluid under gravity, there is an external force due to gravity, then you have if F external equal to force per unit mass, then the net force on the fluid equal to minus gradient P. The force per unit volume then is minus gradient P plus rho times F external per unit volume of the fluid. So let us write that out explicitly. Equal to minus gradient of P plus the density of the fluid times F external. Which implies that the gradient of P equal to rho F external for equilibrium. So this is the condition, this is the condition for hydrostatic equilibrium in a fluid. If F external, which could be a function of space of the coordinates, is the force per unit mass of the fluid, you multiply it by the density, you get the force per unit volume, the external force, and you equate it to the gradient of the pressure, and that gives you the condition for static or hydrostatic equilibrium in this case. Now immediately you see that when you have a gravity, fluid under gravity, so let us put a fluid in a container and this is the z direction, under gravity, then we see that gradient of P would be equal to minus the density of the fluid times g, because that is the force in the vertical direction pointing downwards, so the minus sign, and that is it here. But this quantity has an x component delta p over delta x, delta p over delta y, the y component, etc., and those are 0. So this implies that delta p over delta x equal to 0, delta p over delta y equal to 0, which means that p is really a function only of z, because this says there is no dependence on x, no dependence on y at all. So this implies that delta p over delta z is the same as dp over dz, because there is no dependence on x and y at all, and this is equal to minus rho g. And of course you can trivially integrate this to write P of z in this case equal to P0, which is maybe the force or the floor of this vessel, minus rho g. which is a statement which is we know immediately that the pressure decreases as you go up and it is the largest here and it decreases linearly as you go up here, the fluid column. So that is the elementary relation which you are already familiar with, but it comes from the more general relation which says the gradient of P is rho times F external per unit volume.